Hi everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the development of microstructure in the iron carbon diagram. So in the previous sessions we have discussed about how to draw the phase diagrams and also how to draw the iron carbon phase diagram. Now we'll see what is the development of the microstructure. That means during the cooling process. So once you heat the metal, after cooling, what happens? Slowly it solidifies. So during the solidification process, what are the changes in the microstructure of the iron carbide diagram? We will see. So that is called the development. How it is being developing during the cooling process. So we'll see step by step what are the microstructures development in the iron carbide diagram. Now generally, phase change will occur with respect to the temperature. So change in the temperature refers to the change in the phase. Similarly, the development of the microstructure also depends upon the temperature. So when the material gets slowly cooled, what is happening? The liquid nature, whatever the liquid nature is there, it will slowly come down into a solid formation. So what is happening from the liquid to solid during the process of changing from liquid to solid? What is happening? There are different changes in the microstructure with respect to the temperature. So that we will discuss in today's session. So generally, if you see in this phase diagram, what is happening? The phase change that occurs upon passing from the gamma region into the alpha plus carbide, that is Fe3. That means where is the gamma? So gamma region is nothing but the austenite. So when the phase is changing from austenite to gamma plus Fe3, that means austenite plus cementite or the carbide, what is happening during this process of changing in the microstructure we'll discuss. Now this change, so wherever the phase change is there, there is the change in the microstructure. If it is in the same phase, then there will be the same microstructure throughout that same phase. But once this phase is changing from another phase to another phase, in the same way the microstructure also differs. So since in this case what is happening, the austenite phase is changing from austenite plus the cementite. So how will be the development of the microstructure? We'll discuss. So at that point, what is happening here? We'll consider the same example at 0.76 weight percentage of composition. That means at this point, this is the 0.76 weight percentage of carbon. So what is happening as it is cooled from a temperature within the alpha region? That means we are trying to cool down. So during the cooling process only, there is change in the microstructure. Is it not? When you heat the system, what is happening? It will get melted and it is converting into liquid formation. Now after waiting for some time and letting the system to be cooled, slowly it is cooling and the liquid nature is getting evaporated and you are getting a solid formation. So during this solid formation, there are a lot of changes in the microstructure internally. So now, since we are considering the example at 0.76% of carbon and we are trying to cool the alpha phase region at 800 degrees centigrade. That means at this point, at 800 degrees centigrade, we are trying to cool the system. So where it starts with the point A. So this particular area we'll try to zoom and we'll see what are the changes of the microstructure or the development in the microstructure at this zone of the iron carbide diagram. So we are trying to draw a vertical line along that point 800 degrees centigrade with a composition of 0.76. So this area we are trying to zoom now. So this is the area where we are trying to find out what are the developments in the microstructure. So the same composition, this is the 0.76 weight percentage of the carbide or the iron. So at this point, we are drawing a vertical line which is parallel to the temperature axis. So this is the dotted line, what I was seeing here. X dash is the vertical line. And through that vertical line, at any point, what are the developments in the microstructure we are trying to discuss now. Now, this is the region where you have the 727 degrees centigrade. That means above and below. That means it is crossing the austenite temperature. So this is above austenite, this is below austenite temperature. Now, at this point, if you take the point A and if you want to try to find out what is the composition or what is the microstructure of that point A at this point, so if you see, you have maximum of gamma variants. Okay, you have austenite percentage very very high at this point. Now, when you come down, that means when you reduce the temperature at some point, so point A is approximately around 800 degrees centigrade. At that point, you have lot of austenite. So you have all the gamma microstructure related to this at this point. Now, coming to some little bit of time, we are trying to cooling the system. What is happening? At some point, approximately around 725 or 700 degrees centigrade, point B, if you go to the microstructure, so this is the microstructure at that point. That means below the austenite temperature. So you're having what is you're having combination of iron carbide, that is Fe3C, as well as alpha, that is combination of pearlite and cementite. So that means there is some change in the microstructure. So in the earlier stage, we have maximum percentage of austenite, all the gamma related microstructure at that point above 727 degrees centigrade. Now slowly if you cool the system, what is happening here? There is a combination of pearlite is coming into picture. So here the pearlite, whatever the pearlite you have, the light orange color you are seeing, so that is the pearlite, and whatever the dark area you are seeing, the dark brown color, so that is the cementite. So you are having the combination of pearlite and cementite, that is alpha plus Fe3C. So like that you are getting some changes or the developments in the microstructure when you are trying to cool the material. Any type of material when you cool, when you once heat and let it down for cooling for some time, what is happening? During this cooling process, there are a lot of changes in the microstructure. So since we are considering at 0.76 percentage, 0.768 percentage of carbon, at that point only we are getting these points. Suppose if you increase the percentage again, suppose at 1.58 percentage at this point, then what you have to do? You have to again draw a dotted line which is parallel to your temperature axis, x bar. Again, at this point, if you want to see some point A at point B, there is again some changes, but the composition is approximately same, but the percentage of combination will be varying. Here, since you are increasing the percentage of carbon, 1.5 percentage of carbon here, then there is an increase in the carbide percentage, Fe3 percentage, and reduction in the pearlite. Like that, you have different compositions depending upon the how much amount of carbide or iron you are giving into this. So like this, there is a development of the microstructure at each and every point depending upon the composition. So at this point, we are trying to find out what is the changes in the microstructure related to the composition. So what is happening in this? Initially, the alloy is composed entirely of the austenite, is it not? Since this area above 727 degrees centigrade, what is happening? You have a lot of austenite is present. This is entirely complete in the complete microstructure. You have complete austenite is there. There is no other pearlite or any pearlite is coming into this picture. Complete austenite you have. That's why you have a solid structure of complete austenite here. So at what composition again? At 0.76 weight percentage of carbon at that point. Now once this system is slowly cooled, what is happening? It is crossing that 727 degrees centigrade. So that means up to point B, there is no change in the microstructure. So once it is touching the point B, what is happening? Slowly it is converting that cement austenite is slowly converting into pearlite and the ferrite. Combination of these three. Upon crossing. So up to this red line, what are the 727 degrees centigrade you are seeing? Up to this line, there is no change in the microstructure. But once it is crossing the austenite temperature. So what is the austenite temperature for this iron carbon diagram? It is 727 degrees centigrade. at 0.76 weight percentage of carbon. Okay, so these all the things you have to remember. What is the weight percentage as well as the austenite temperature for iron carbon only. So again, if any other combination is there, then again these compositions or austenite temperatures will vary. But for this iron carbon, we have 0.76 weight percent at 727 degree is the austenite temperature for this iron carbon. So once it is reaching that 726, that is called the eutectoid temperature. At this eutectoid temperature, what is happening? Slowly the changes are occurring inside the material, and there is some development in the microstructure after crossing that eutectic temperature. That means upon crossing this point, what is this point? The point be your austenite. Whatever the austenite you are seeing above the eutectic temperature, the austenite is being transformed. Slowly it is being transforming. That's why you can see there is a lot of changes in these two structures. After crossing that eutectic temperature, that is 727 degrees centigrade, whatever the austenite is there above that eutectic temperature, slowly this austenite is being transforming after crossing that eutectic temperature. That is very, very important. So that we have shown in this phase diagram. How is the development? Now, the microstructure for this eutectic steel that is slowly cooled throughout the eutectic temperature consisting of alternate layers. So, if you see closely, if you observe, after crossing that eutectic temperature, that is 727 degrees centigrade, what is happening in the microstructure? You can see some layers are being formed. That orange color and blue color layers, one by one after the alternate layers you are trying to see in the figure. So, what are these layers? So, these layers refers to that there is some development in the microstructure. So, it is having some pearlite and also the cementite Fe3C. So, like that you have to observe what is happening, what is the development in the microstructure. So, after crossing the eutectic temperature, slowly the austenite is being transformed. And if you observe clearly, you have alternate layers. So, this blue, orange, these are refers to the alternate layers or the lamella of the two faces. So, what are the two faces you have here? Alpha and Fe3C. So, these are the alternate layers are arranged one after the other so that you can see the difference in the microstructure above and below the eutectic temperature. So, the microstructure represented in this figure, that is the point B, this is called as a pearlite. The complete microstructure, whatever you are seeing, is called pearlite. And this austenite. Okay, above the eutectic temperature. So, what is the eutectic temperature here? The red line, whatever the C, eutectic temperature at the 727 degrees centigrade. So, 727 degrees centigrade is the eutectic temperature of iron carbon at what percentage? At 0.76 weight percentage of carbon. So, this is what is reflecting in the development in the microstructure. So, at the eutectic temperature, there is no change or there is no transformation of that austenite microstructure. But once it is crossing the eutectic temperature, there is the transformation of austenite. Slowly, the austenite is being transformed into pearlite. So, again, what is pearlite? It is a mixture of alpha and Fe3C. Okay, it is being arranged alternately. So, whatever the thing you are seeing here, alternately blue, orange. So, this is the combination of alpha and Fe3C. And the complete microstructure of this alternate layers which are being formed is called as a pearlite. So, above you have austenite and below the eutectic temperature you have a pearlite. So, this is how it is being developing. Okay. And if you further go and if you see through the photo micrographic, if you see the same material with the microscopic view, you can see the arrangement of this pearlite. So, what are the alternate layers we are seeing? So, this is called the pearlite microstructure consisting of alternate layers of ferrite and Fe3C. So, See, you can clearly see the black, white, black, white, black, white. So these are called alternately they are arranged. Okay, so that's why the layers of ferrite, the light phase. So wherever the light phase you're seeing, so these are called the layers of ferrite. Okay, layers of ferrite, and the dark are called the Fe3C. So the dark and the light are called ferrite. And combination of these two, alpha plus Fe3C, is called pearlite. So this is how you have to remember. So by seeing any microstructure, it is very easy for us to identify which type of material is this, or what is the microstructure of this. So if any material is having alternate layers having the combination of alpha and Fe3C. So here alpha is nothing but the thick layers. So what are the thick layers you are seeing here is called Fe3C, and whatever the thin layers you are seeing, that is called F. The light thing is called ferrite. So combination of these two is called as a pearlite. So this is a combined a pearlite microstructure. That's it. Austenite is being converting into a pearlite microstructure during the iron carbon diagram when the system is being cooled from the eutectic temperature. And if you now see clearly what is happening, so this is what the austenite composition we have. It looks almost like a solid. So okay, since because there is no other material, completely austenite is involved above the eutectic temperature. There is no other combination here. But when you cool the system slowly, what is happening? There is some combination of Fe3C and alpha particles here. So it is a combination of pearlite. So these alpha and Fe3C are arranged parallelly to each other, one after the other. Alternatively, they are being arranged. So this is the ferrite. What are the things you are seeing? The light thing, that is the alpha. And what are the dark area you are seeing in this microstructure? That is called Fe3C. So combination of both alpha plus Fe3 is called as a pearlite. And the solid things, whatever the solid things you are seeing in this, it is completely of austenite. There is no other combination. Complete austenite you are having. So that is what there is a development in the microstructure of this iron carbon diagram during the cooling process at 0.76 weight percentage of carbon. So it is converting from austenite to pearlite. Next, that is about development in the microstructure of the iron carbon diagram. Next, coming to the hypoeutectoid alloys. So what are the hypoeutectoid alloys? So in the previous sessions we have discussed about what is eutectoid, eutectic and proeutectic. Now in this session, you're going about the new terminology that is called hypoeutectoid alloys. So what is hypoeutectic alloys? So the microstructure of the iron carbon diagram, alloys having other than eutectic composition. Okay, if any iron carbon diagram, in this composition, if any other composition rather than the eutectic composition. So eutectic composition we have seen in the previous sessions. So if it is not having, any alloy is not having other than eutectic composition, then that is called as a hypoeutectoid alloy. So that we are going to extract now from the iron carbon diagram. So what are the alloys which are having now other than the eutectic composition, then those are called the hypoeutectoid alloys. So what are those hypoeutectoid alloys now? We will see the percentage. Now up to 0.76 percentage, we are trying to get the eutectoid composition in the iron carbon diagram, is it not? But below 0.76 percentage, what are those alloys or what are those compositions means? Those are called hypoeutectoid alloys. So till now we have seen up to from 0.76 percentage to 6.78 percentage of carbon. But what is happening below 0.76? So above 6.78% we have graphite. So that we have discussed in the previous sessions. But between 0.76 and 6.70 we are getting the carbide, and after 6.70 we are getting graphite. Now from 0 to 0.76 weight percent, what is happening? So what are the alloys are having in between this 0.022 to 0.76 weight percentage? Those alloys are called the hypoeutectoid alloys. So those hypoeutectoid alloys we are trying to identify, and what is happening in the development in the microstructure we are going to extract now from this iron carbon diagram. So the composition which is in between 0.022 and 0.76 weight percentage is termed as hypoeutectoid. Above 0.76 we call eutectic composition. Okay, the composition between 0.022 and 0.76 weight percentage of carbon is termed as hypoeutectoid alloy. Now this hypoeutectoid alloy, after cooling, so what is happening and how to represent the microstructure, we'll see. Now for the same iron carbon diagram, at this position we are trying to do. So why? Because this is the 0.002 weight percentage. These 2 points, 0.022 weight percentage of carbon. So at this junction, again the eutectic temperature was what? This is 727 degrees centigrade. So the eutectic temperature is 727 degrees centigrade. And what is the percentage composition here? 0.022. So this is the 0.022 weight percentage of carbon. So at that point, again you have to draw a vertical line which is parallel to the temperature. And from that point, at any point, if you want to see what are the changes, what are the developments in the microstructure, means at some points, at point C, D, E, F, at these 4 points, we are trying to identify what is the microstructure, how is the development in the microstructure. So if we see the point C, completely again in the previous thing, we have austenite, complete austenite is there. There is no another mixture here. That's why you have all the gamma, that is the austenite particles. At this point means suppose it is around 870 degrees centigrade. Now slowly cooling the system, at point D you are reaching, this is below 800, approximately around 780 degrees centigrade. So what is happening? What is happening at 780 degrees centigrade? So if you see here, you have the combination now. Now carbide is coming into picture. For the austenite, in the previous, we have complete austenite. Now slowly after cooling, since the carbide composition is adding into the alpha austenite material, slowly there is some orange thing we are seeing here. So these are the alpha particles. That is, some ferrite is being involved in the austenite. So combination of both alpha as well as the austenite, alpha plus gamma. So you have ferrite and austenite after reaching to 870 degrees centigrade. Now if you still further come down, if you reduce the temperature, that means the system is being cooling. So what is happening? There is an increase in the percentage of alpha particles, that is the ferrite particles here. So slowly coming down, cooling the system, there is some increase in the area of the alpha zone. Of course, there is a gamma zone, that is the austenite zone is there, but the domination is being increasing slowly when the system is being cooling. So up to point eutectic temperature, it is slowly converting. But once it is crossing the eutectic temperature, that what is the eutectic temperature here? 727 degrees centigrade. After crossing that eutectic temperature, what is happening is there is some drastic change in the microstructure. Now, if you see the point F, what is happening here? There is a lot of change. Again, you have here alternate layers of alpha and Fe3. So what is the alternate layers of Fe and alpha and Fe3? That is called pearlite. So there is some portion of pearlite here. There is some portion of pearlite. Here also you have some pearlite combination. And here you have some empty space. So this is called as a pro-eutectoid. That means before eutectic temperature, before eutectic formation, it is called as a pro-eutectic. Okay, slowly converting into eutectic, it is starting the initial stage of eutectic temperature, that is called as a pro-eutectic. So you have here again the alpha, and here you have carbide. So wherever you see the dark area, that is dark blue region, that is called the Fe3C, the carbide area you have here, this and this. And wherever the orange thing you are seeing, that is the alpha particle, that is the ferrite particles. So here you have the again the domination of the ferrite is more. And again some area is arranged alternately with ferrite and the carbide. So the alternate arrangement of this ferrite and pearlite is called as a pearlite. Okay, so this is how there is some development in the microstructure for the hypoeutectoid alloys. So what is the hypoeutectoid alloys? Where the composition is ranging between 0.022 weight% and 0.76 weight%. That zone, that area where the material is being changed or the microstructure is being varied, at that zone is called as a hypoeutectoid alloys. Beyond 0.76%, that is called eutectoid alloys. And again after 6.70, that is called as a graphite alloys. So like that in the iron carbon, you have a lot of compositions, different sections you have. From 0 to 0.76, you have hypoeutectoid. After crossing 0.76 to 6.70, you have the cementite, that is the carbide formation. And after crossing that 6.70, you have the graphite area. So like that, three divisions are there. And again, what you have, the eutectoid temperature is also there, that is, which is parallel to your composition axis. Above eutectoid temperature and below eutectoid temperature. So above eutectoid temperature, you have a lot of presentation of austenite there. Now, once it is crossing the eutectoid temperature, what is happening? There is a lot of changes in the microstructure. You have the combination of ferrite, you have the combination of alpha particles, you have some area of pearlite. So all these are happening below the austenite eutectic temperature only. So that's why you have to identify where is the which is the point where the complete material is being changing. So at this point, this is the point that is called the eutectic temperature at 727 degrees centigrade. So after crossing this 727 degrees centigrade, then you are getting a drastic change in the microstructure. So like that, you have to identify at each combinations, at each weight percentage, what are the changes or what are the developments in the microstructure with respect to the iron carbon phase diagram. So at about 875 degrees centigrade, what is happening slowly? What are the points we are discussing? That point A, B, C, D, and E, F. So at point C, that is at 875 degrees centigrade, it is having completely of gamma, that is the austenite particles. There is no change. But once slowly you are cooling the system, slowly one by one, the alpha particles are being adding into the system. And still, if you further go, there is some raise in the alpha, that is the ferrite particles. And if you're crossing the eutectic temperature, there is a huge, vast change in the microstructure, which is having the combination of your ferrite and the austenite. So that is called the pearlite region. So at these weight percentages, you can see the drastic change in the microstructure or the development in the microstructure. So this is how, if you see the microstructure, what are the changes you can see here. So at this point, you have a complete austenite. That's why you have the solid region. So like similar to the eutectic thing, what you have discussed in the previous at 0.76%. Now at this point, this is the 0.022 weight percentage of carbon at this point. So what is happening? So here you have complete 100% of austenite. Here, this is 100% of gamma. And slowly, if you reduce the temperature, so you can identify some small portions of alpha. That is, you have some ferrite. And if you still further reduce the temperature, you can easily identify the space here. This is again the same ferrite you have. Now, once it is crossing, up to this, you can have this microstructure. Now, once you cross this eutectic temperature, so what is happening? There is vast change, drastic change. Now here you have pearlite. Pearlite is nothing but the alternate arrangement of alpha plus Fe3C. This is the pearlite. And proeutectoid, wherever the white patches you are seeing, the white thing. So this white. So this is the proeutectoid for ferrite. That means before eutectic reaction, you are getting this proeutectoid. So this is how the development. So this the empty is the white region you are seeing here. So this is the proeutectoid. Okay, and this is the pearlite. That is the dark thing. Here you can see this pearlite. So like this, there is a development in the microstructure during the cooling process of the hypoeutectoid alloys. Now, thus the ferrite phase will be present both in the pearlite and also the phase formed when cooling. So, when cooling only, when any system during the cooling process only, you can observe all these changes in the phases or all the changes in the microstructure. So, while cooling through this alpha and gamma phase region only, you can observe different formations of the microstructure. So what are the white areas you are seeing in the microstructure? That is called as a proeutectoid. And what are the dark thing you are seeing in the microstructure? This is called as a pearlite. Pearlite, again this pearlite is a combination of alpha plus Fe3C, that is the ferrite plus the carbide. Fe3 is nothing but the carbide and alpha is nothing but the pearlite. So the ferrite plus Fe3C is called the pearlite. So this is the pearlite. You have Fe3C plus alpha. That is the ferrite. Ferrite plus carbide is called pearlite. And proeutectoid ferrite is nothing but before eutectic you are getting this empty. So this is how you have to identify the developments of the microstructure. Now coming to the isothermal means at constant temperature. At constant temperature, what is being varying? So what are the being transformations? So here, conditions of constant temperature is termed as isothermal. So what is isothermal means? When the temperature is constant, then that is called as an isothermal reaction. Now, the plots, what are the plots we are showing here? These are refers to isothermal transformation, or sometimes it is called as a TTT plots. That is temperature, time, transformation. So how it is being transformed with respect to time and temperature. So triple T, 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 T plots. Time, temperature, transformation. So how it is being transformed with respect to time, temperature. So that is called as a isothermal plots or triple T plots. As you see in this figure, so what are the things we have discussed in the iron carbide diagram? The same thing we are trying to represent in the TTT transformations, triple T transformations. So how it is being starting, at which point is being, you are getting a midpoint, and after that what is the end point of the transformations. So everything will be put into this plot to show what is happening in the iron carbide diagram. So if you see the x-axis, you have the time, which is in seconds, and y-axis is the temperature. Now the eutectic temperature is about 727 degrees centigrade. Okay, that you are drawing here. This is the eutectic temperature. That is the, we are representing here eutectoid temperature. So above eutectoid temperature, what is happening in the phase diagram? The austenite is stable, is it not? You are completely getting the gamma microstructure. There is stability in the austenite formation above the eutectoid temperature. Now, after crossing that eutectoid temperature, what is happening? There is unstable of the austenite. That means slowly the austenite is being transforming. So this austenite is being transformed into pearlite. So what is the starting point of pearlite? If you see here, the red curve, what is the red curve you have? This is the beginning of the pearlite. So beginning of the pearlite starts below the eutectoid temperature. That's why you are getting this red line. Starting with this point, immediately it is starting below the eutectoid temperature. So this is the starting point. So if you again draw a parallel line here, you are getting it some what is the weight percentage here, but what time it is being started. So that's why beginning curve of pearlite. Now after some time, what is happening? The blue indicates for the 50% completion of curve. That means 50% of transformation of the austenite from to pearlite. This the austenite is being 50% transformed into pearlite from austenite. That is the blue indication. Now coming to the green curve, it indicates the completion of the pearlite. So what is happening? See, you can see here below the detected temperature, you have three curves. Red indicates for the starting, blue indicates for the midpoint, and green indicates for the complete formation of the pearlite. So since in the phase diagram we have seen slowly the austenite is transforming into pearlite below the eutectoid temperature only. That's why what are the three curves you're drawing in the TTT plot has to be drawn below the eutectoid temperature only. So below the eutectoid temperature only you have all these curves. Now, if the curve, the red curve, if you start drawing above the curve, so it is exactly at this starting point 0. At 0 time, it is being starting. At some time of interval, it is reaching to the midpoint, that is at 675 degrees centigrade. At that 675 degrees centigrade, you are getting 50%, 50% completion of pearlite. The austenite is being transformed 50% at 675 degrees centigrade. Now, still, if you reduce the temperature, what is happening? It is completely transforming into pearlite. That is, you are getting 100% of pearlite, and this is called the end point. End point of pearlite. That is, you are still reducing the temperature. That's why, if you again drop on this, you are getting exactly at this point. Though this curve refers to the complete pearlite, where the austenite is being completely transformed into pearlite. So this is how you have to represent the TTT plots with respect to the iron carbide diagram. So in the iron carbide diagram, you are showing the microstructure of each zone, each phase, how it is being transforming. But the TTT plots, that is how the plots are being transformed with respect to time and temperature. So those are called the TTT plots. That is called isothermal plots. So when there is a constant in the temperature, constant temperature refers to the isothermal. So again, these curves sometimes are called as the C curves and S curves. Why it is called C curve and S curve? If you see the shape, so it is almost similar to S symbol. And here you can see it is in the form of a C symbol. So that's why these TTT plots are also called as a S curves or C curves. So TTT plots refers to S or C curves. So in some books it is shown as C curves, or in some as S curves, or some as TTT or isothermal. So all this refer to the same. How we are representing the starting and end point of the conversion or the development of the microstructure of any alloy represents with the time temperature transformation. So this refers to the TTT plots of the iron carbide phase diagram. So if you consider the iron carbide of the eutectic below eutectoid, so what is happening? What are the changes in the eutectoid reaction? That means you're taking at 0.76 weight percentage of carbon. So when it is transforming into alpha plus Fe3C, is it not? The austenite is transforming into ferrite plus carbide or the cementite. So this is how it is being transforming with respect to the eutectic reaction. So the carbide and ferrite combination refers to the pearlite, and this gamma is our austenite. During the cooling process, this austenite at 0.7776 weight percentage, it is being transformed into Pearlite. So again, Pearlite is a combination of alpha at 0.008% plus ferrite at 6.708%. So like this, you have to write the equation in order to show the how it is being transformed from one phase to another phase. And these are some of the temperature plots. What I told, these are in the S shape, starting, midpoint, and endpoint. This is the starting point, midpoint, and endpoint. Since the shape is in the S formation, that's why this is called as a S type of curves. Whatever the TT plots are there, since these are being in terms of S shape, that's why these are called S-shaped curves. And from this S-shaped curves, we get the how much percentage completion of the transformation. At this point, if you want to see, it is 50%. At this point, it is 0. That is the initial point. At this is called end point. Okay, end point. Like this, same 0%, 50%, end point. 0, 50, and end point. So this refers to the percentage, and this refers to the time. So like that, with respect to time, temperature, how it is being transformed of the phase diagram can be applied with this. And for a more convenient way representation, both the plots have to be drawn, okay, and it has to be collide with each other. So it has to be exactly overlapped where you are getting the end point and starting point and where midpoint you are getting. So it is very easy for us to identify which is the end point, which is the starting point, which is the midpoint. With respect to the percentage of completion also, we can get through this TTT plots. And two solid curve plots are, one of it is, see, if you want to have the 50% completion, then you have to go with this blue. Here you are getting the 50%. At what temperature you want to get means, just draw a line like this, you can get the temperature value. Similarly, if you want to get the 100% completion of Pearlite, then you have to go with respect to temperature at this point. So this is the 100% completion. So if you draw this here, you'll get the temperature. So wherever the conversions are there, you'll get below Eutectoid temperature only. Above Eutectoid temperature, you won't get any conversions or any developments in the microstructure. So that you have to remember carefully. Now, coming to the other process, you have the annealing process. So what is annealing? You have to heat. Annealing is nothing but heating of the material. So once you heat the material, what happens? If any uneven things are there, so suppose if this is the material, I have a uniformity in the material, but somewhere I have some gap like this. There is no uniformity. Some elements are moving somewhere. That means there is weak in that area. So there are some gaps. So what you have to do when you heat the system, when you heat the alloy or element, what is happening? Wherever the disturbances are there, these are again re-uniformed and they will look like this. So what are the conversions are there? It is being reformed. It is coming into a uniform state. Okay, so this process of heating of the element to convert non-uniform element into uniform material is called as a annealing process. Is it clear? So the term annealing refers to the heat treatment in which the material is exposed to elevated high temperatures for an extended time period. Is it not? You have to heat the system for some time, then only you can get the even structure. And after heating, you have to let it down to slow cooling process. You should not do immediate cooling. Again, if you do immediate cooling, what happens? The formation of cracks, everything will happen. It extends the wear also. So that's why you have to heat to an extended temperature and slowly let it down to cool. Then you'll get the uniformity in the material. Whatever the uneven things are there, they'll get into uniformity in the structure. So what is the importance of the annealing means? It will try to relieve the stresses. That means if any stresses are there inside the body, these can be relieved. And also increases the softness, ductility and toughness. And also specific microstructure. In order to get the specific microstructure, you have to do the annealing process. So these are the three main criteria you have to remember. First, what is annealing means? Heating of the system in order to convert non-uniformity into uniformity. And why you're doing this heating process means in order to get stress reliefs, in order to get specific microstructure, in order to increase the ductility or the toughness. These are some of the things where annealing is important. Also, if you want to enhance the properties of mechanical properties, so annealing is one of the important process for enhancing the mechanical properties. And what are the three stages involved in the annealing means? First process is heating to the desired temperature. So any material, so different materials will have different melting points. So to the extended temperature, we have to heat first. Then what you have to do? We have to soak the material after heating, and then you have to do the cooling process. So these three stages you have to do. The first one is the heating to the desired temperature, second one is the soaking, and third one is the cooling. So these are three stages you have to do in the annealing process to improve or to enhance the mechanical properties. And if the rate of temperature changes is too great, that means the temperature gradient and internal stresses can be reduced. So this is very important. If you want to reduce the internal stresses inside the body, then you have to increase the temperature of the given system. So annealing temperature is different for different type of materials. So same material will don't have the same annealing temperature. So different materials have different annealing temperatures. So depending upon the material, you have to select the temperature in order to relieve all those stresses or to increase the mechanical properties or the enhance the mechanical properties. So why stress relief? So internal stresses are subjected to the body during the action of forces. So these internal stresses can be relieved during the annealing process. So plastic deformation process such as machining and grinding. So during this machining and grinding process, what is happening? There is some deformation. So this deformation can be transformed or relieved with help of the annealing process. So non-uniform cooling of a piece during the fabrication process. So a proper cooling is, if it is not done, again there is some change in the fabrication. So that's why this has to be elevated to some temperatures in order to relieve all those stresses. And phase transformation. So one phase to other phase. So it is transforming to one phase to other phase. Again, the temperature plays a key role here. So distortion or wrappage or any other properties which are being coming down can be increased with this annealing process. So these are some of the things you have to remember in order to enhance the properties of the any type of alloy. Again, coming to normalizing. So annealing and normalizing are different to each other. So what you are doing here, normalizing. So steels generally have been plastically deformed. So generally some deformation is there during the machining process. So what is happening during a rolling operation, which consists of different types of combinations. It is having a pearlite or fairlight or cementite or carbide, different compositions. So these can be irregularly shaped. They're not. Some material will have some irregularity in shape. So if you want to make it is uniformity, if you want to make the system into uniformity, then you have to use the normalizing. So in the name itself, you have normalizing. So this normalizing is useful to make the system into a correct uniformity or the regular shape. The irregular shape can be converted into regular shape with the help of the normalizing. So you have different grains inside the body. So if you arrange these grains in a similar fashion, then the unshaped, the irregular shape can be converted into regular shape. So this process can be done with the help of normalizing process. So hardenability, if you want to increase the hardenability of the material, if you want to increase or enhance the hardness of the material, you have to do this quenching treatment process. Okay, so it transforms again the pearlite, ferrite are converted into austenite. So this process of conversion of those steels into the austenite, transformation to austenite, these are called the hardness. So how you are getting sudden cooling, we should not do. Slow process of cooling you have to do when doing the manufacturing process. So ability of an alloy to become hard, okay, so that is called the hardenability. So this can be achieved with the help of heat treatment process. So hardenability is not only refers to hardness, it has to resist to indentation also. So different application of forces are applied on the body. So all this has to be resist. So during the manufacturing process, heat is generated, forces are applied, different applications are applied on the body. So all this has to be resist within the body. So for that you have to do the hardness. So that is very, very important to achieve the required target. So now, in order to have how to draw the developments of the microstructure, how to identify what are the different compositions, what is happening at each stage, what is the eutectoid temperature, how the microstructure is changing above and below the eutectoid temperature, and what are the applications to get the uniformity in the structure can be get from these references, that is the introduction to physical metallurgy, essential of material science and engineering, material science and metallurgy. So these are some of the references where you can get all the information what we are discussed in today's class. Okay, so material science and engineering. So it is very easy for us to differentiate the microstructure. By seeing the microstructure, it is very easy for us to differentiate with respect to the composition, what type of material, what type of microstructure, how much percentage composition of ferrite is there with respect to pearlite. All these things can be. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.